Good afternoon to all of you. Welcome to the second sessions of Signals and Systems for GATE exam. So in session 2 we are going to discuss about the classifications of systems. We are going to discuss this particular topic in today's session. In yesterday's session we discussed about the introduction to signals, properties of signals, and problems based on the properties of signals. These are the topics which we have covered. In today's session, we are going to cover the various systems and we are going to discuss that. So this is the syllabus related to this. So in signals and systems, in order to find the response of a given system, we require some standard signals like unit impulse, unit step, and unit ramp. So why these are called standard test signals is, for example, if there is a sudden change in input, whether that sudden change in input is going to give us the system output in what manner can be identified by these standard test input signal like unit impulse function. Suppose if my input is changing gradually, how my output of the system is going to change. I am going to test by making use of such functions. So we are going to discuss first about these unit impulse, unit step, and unit ramp. The first standard text input signal is the unit impulse signal. So one of the more useful functions in the study of linear system is a unit impulse function. An ideal impulse function is a function which is zero everywhere, but at the origin it does have an amplitude and it is infinitely a high value. However, the area of the impulse is finite. That we are going to prove that the area of the impulse is a finite value. The unit impulse function is given by the equation. It is also called as Dirac delta and it is given by the equation delta of t is equal to 0 for t not equal to 0, and it is undefined. That means it will have an infinite value for t is equal to 0 and has the following special property. Let us try to understand what is that special property. It is minus integral minus infinity to infinity delta of t dt is equal to 1 is a special property of a unit impulse function. So here a consequence of the delta function is that it can be approximated by a narrow pulse. You observe here we have a narrow pulse and you are on the x-axis you see the width of the pulse and this is the height of the pulse. As the width of the pulse approaches 0 while the area under the curve is 1. For example, you take a generalized limits on the width like minus epsilon by 2 as the lower limit and plus epsilon by 2 as the upper limit, and the height is 1 by epsilon. Now you can compute the area as this height into width for this particular narrow pulse. If you compute the product of height into width, epsilon by 2 minus epsilon by 2 will result in a value of epsilon. Multiply that with the height which is 1 by epsilon. So epsilon divided by epsilon is going to give us a unit area. That's what the meaning of giving a unit area. And the strength of this unit impulse function is shown by a bold line here. That is showing the amplitude at t is equal to 0. The area under an impulse is called its strength or weight. For example, here we have a shifted impulse of amplitude 5 is represented by 5, whereas here it is having an amplitude of 1 only. So on the extreme left hand side, you observe a unit impulse function with an amplitude of 1. So it can be represented graphically by a vertical arrow. Yes, we are showing a vertical arrow here. An impulse with the strength of 1 is called unit impulse, and this is an impulse with an amplitude of a shifted impulse of amplitude 5. And often we find the use of number of impulse functions, unit impulse functions, which is termed as unit impulse train. The unit impulse train, what is it? It is a sum of infinitely uniformly spaced impulses. So you observe on both the right hand side and the left hand side, you have number of impulse functions, impulse amplitude with unity amplitude, both on the left hand side and as well as right hand side, as it is getting extended from n is equal to minus infinity to infinity. We have this is termed as a impulse train, as you can observe here in this particular plot. Now let us try to understand the different properties of an impulse function. Suppose we are given delta of t. The delta of t is an even signal. So yesterday we discussed about the property of even and odd signals. So a signal x of t is said to be an even signal if x of minus t is same as x of t, then we can say that as an even signal. Now what we can do is, we are given an impulse function delta of t. Now substitute t is equal to minus t, and then if you work out, delta of minus t will result in a delta of t, and hence it is an even signal. And if you take an impulse function, and yesterday we computed the property which is energy of a given signal, which is given by energy of x of t is equal to integral minus infinity to infinity mod of x of t whole square dt, that is amplitude square. If you remember, yesterday we had worked out a number of problems for a given signal, how to find the energy and how to find the power for a given signal. We had done those problems. So with that particular property, we can observe that the given impulse function is neither energy nor a power signal. So, and here is again another important property is weight or strength of an impulse. Suppose an impulse function is multiplied by an amplitude a naught, then we can find area of the weighted impulse y of t by taking the equation integral minus infinity to infinity y of t dt, and we can substitute in place of y of t a naught delta naught t, that will result in a value of a naught. Now the question is, why we got a naught? As per the special property of an impulse function, integral minus infinity to infinity delta of t is equal to 1. Hence we replaced this integrand with a 1 value, that gave the result of the area of weighted impulse y of t as a naught. So it is very clear to understand this particular property, area of a weighted impulse, which resulted in a constant value of a naught. Now let us take another important property of the impulse function, which is called scaling property. The scaling property, this particular scaling property of the signal, yesterday also we discussed. So if a signal is there and it is time scaled by a factor of a, then it is called a scaled signal. Here we have delta of a multiplied with t minus t naught, and the scaling property is going to give us mod of 1 by mod of a delta of t minus t naught. And based on this property, we may do simple problems like, suppose you are asked to find out delta of minus 2t, then as per the property 1 by mod a, here in place of a we have minus 2. As we are taking modulus for minus 2, modulus of minus 2 is going to result in a positive value, and we got 1 by 2 delta of t. So we can simply apply the scaling property. And the second example is the exact replica of the scaling property of the impulse function, which is given by delta of 2t minus 3, and in place of a we have 2. But here you do observe it is not exactly of the form a into t minus t naught. It is of the form at minus t naught. So first of all, in this particular step, you try to convert into the standard form of a into t minus t naught, and hence you take 2 as a common factor. Then you are going to get 2 multiplied with t minus 3 by 2. And now you can straight away apply this particular property, which is 1 by mod a. In place of a, we have 2. So hence we got 1 by 2 delta of t minus 3 by 2. So if you are thorough with these properties of the functions like impulse function, it is very easy for us to find the apply the scaling property and find the values like delta of 2t minus 3 or any given signal. For any given signal, we can solve it very easily. And another important property is if a impulse function is multiplied by another function, that is going to result in a value of phi of 0 multiplied with the delta of t. Let us try to understand this particular function, how we got the multiplication of phi of t delta of t as phi of 0 delta of t is, here you consider the function phi of t and multiply it with an impulse delta of t, which is given by phi of t delta of t, and phi of t is continuous at t is equal to 0, and we apply the equation integral minus infinity to infinity f of t phi of t delta of t dt, and you can substitute, you take phi of f of t, phi of t. It can be multiple functions, not only phi of t as one function. You may have multiple functions of time that may be multiplied with the delta of t. So here you observe that at time t is equal to 0 only, the impulse function has an amplitude. At all other values of t other than 0, you have a 0 amplitude. As a result, taking that simple concept, if you apply that, you observe that your f of t does exist for only t is equal to 0, and hence here you will get f of 0 multiplied with phi of 0. Hence, the multiplication of phi of t with the delta of t resulted in phi of 0 delta of t is a scaled impulse, and as this being you can say phi of 0, because we are substituting 0, it's like a strength or amplitude you are going to get. So this is what the multiplication property of an impulse function. Let us move on to another important property, which is called sampling property. And if f of t is a given function and delta of t is sampled by a factor of t naught, and again as usual applying the property delta of t minus t naught exists only at particular time t is equal to t naught. At all other time values, at all other t, you will have delta of t minus t naught as 0, and also delta of 0 is equal to 1. That means at origin you will have delta of 0, which is unit amplitude, and taking these two into consideration, we may simply prove the sampling property f of t delta of t minus t naught over the integral minus infinity to infinity as f of t naught, which is called simply the sampling property. Now let us take a graphical representation of this. We have seen the multiplication property. Now we are given multiplication of x of t with delta of t minus t1, and as per the multiplication property, here we have to substitute t is equal to t1 in x of t. So substituting t is equal to t1 in x of t will give us x of t1, and as usual this delta of t minus t1. And if we plot the x of t signal here, x of t signal is plotted here, and as at time t1 it has this much amplitude, and we may take that as x of t1 and plot the delta of t minus t1. The meaning of delta of t minus t1 is that at time t is equal to t1 only it has an amplitude that exists. So at time t is equal to t1, for delta of t minus t1, here we have shown the amplitude with an arrow mark. You observe that this notation we discussed already, and now you multiply these two, x of t multiplied with the delta of t minus t1, that resulted in again x of t1, and hence we are able to show this particular property. Now let us take a simple numerical example for this one. So 2 sine t multiplied with the delta of t minus pi by 2, and this is of the form again x of t multiplied with the delta of t minus t1. Now in place of t1 we may substitute pi by 2. So if we substitute pi by 2 in place of t here in the sine function, 2 sine pi by 2 multiplied with the delta of t minus pi by 2, and as we all know sine pi by 2 is 1. We may multiply 2 with 1 and then multiply with the delta of t minus pi by 2, resulted in a value of 2 into delta of t minus pi by 2. So this particular multiplication property, we can make use it in the sampling property also. So what is it? Again, integral minus infinity to infinity. The given function is x of t multiplied with the impulse delta of t minus t1 dt. As per the multiplication property, at time t we need to substitute t1. So we substituted in x of t at t is equal to t1. We got x of t1 here and delta of t minus t1 dt. And as it is a like a amplitude value, we have brought that, and it is independent of dt variation. So you can bring this x of t1 outside the integral, and you observe x of t1 integral minus infinity to infinity delta of t minus t1, and delta of t minus t1 is equal to u is 1 over the integral minus infinity to infinity, and this is what the property of your impulse function. As a result, we obtain x of t1. That is what a simple proof that we can show it for the sampling property. Now let us take an example problem on the sampling property. You try to understand what is the given equation. We are given cos of 2 pi t delta of t minus 1.2 plus u of t delta of t minus 3. Of course, we are going to discuss about this u of t right now. So time being, we will take the sampling property of delta t resulted in so as per the property, multiplication property, what is that we can do is, here it is of the form delta of t minus t1. In place of t1, we need to substitute 1.2. As a result, cos of 2 pi multiplied with 1.2 is this first term. Again, that is multiplied with delta of t minus 1.2, and here again we have delta of t minus t1 and u of t is there. What is to be done now? Yet t is equal to t1. So here for the second term, the t1 value is equal to 3, that you can observe here in delta of t minus t1, t1 being 3, we will substitute that value of 3 in u of t. That will result in u of 3 multiplied with the delta of t minus 3, and we will integrate over the limits minus infinity to infinity cos 2 pi t delta of t minus 1.2 and u of t delta of t minus 3 dt, and as per the integral minus infinity to infinity delta of t minus T1 is equal to unity, we may easily find the value of this integrand as cos 2 pi. Here T1 is substituted as 1.2. 2 multiplied with 1.2 will result in a value of 2.4 multiplied with pi plus u of 3. And one can easily find the value of this as u of t is equal to 1. That property we are going to discuss just shortly. So we will discuss that. So the final result is cos of 2.4 pi plus 1. So this is a simple example problem based on the sampling property. Again, another typical example problem we may see here, we are given the integral. Now, why we are saying it's a typical or a tricky problem is, whenever you will get such a impulse function, you should be very cautious of observing the given limits. Now, the function given is delta of t minus 3, but the limits that are given are minus 2 to plus 2. Now, why we are saying we should be cautious is, you observe, just if you plot this particular delta of t minus 3 function, you observe that in between minus 2 to 2, you do not have delta of t minus 3 any amplitude value. The amplitude value of delta of t minus 3 exists only at t is equal to 3, which is outside this integral value, and hence one can easily say I is equal to 0. That is the reason why I am saying, when you are solving such impulse function problem, try to observe what are the lower and upper limits of your integral, and whether it is inside the inside this time interval, or whether the function is outside the time interval. You need to observe thoroughly, then you will not make any mistake. Let us take again another simple problem. Now you are asked to find out the integral value of this integral minus infinity to infinity, the function 2 cos t by 2 plus t square and delta of t minus pi, and this is of the form x of t multiplied with the delta of t minus t1. Now, what property is to be applied here? What property we have to apply? We can, just now we did a problem, we can understand that we can simply apply the property of x, integral minus infinity to infinity x of t, delta of t minus t1 is x of t1, and we can easily apply that property, and then in place of t1 we have pi. So hence you may see this 2 cos pi by 2. Observe that here what we did is, we have taken 2 as a common factor, hence 2 cos of t by 2 plus t square by 2, if I take 2 as a common factor. So that's the reason why here you observe 2 cos t by 2 plus t square by 2, and t being that t1 value being pi, we are substituting that value of t is equal to t1, which is pi here. So it will result in cos pi by 2 plus pi square by 2 within the parenthesis, that multiplied with 2, that will result in a value of pi square. This is how we can easily find. At the beginning, it seems to be a tougher one, because if we replicate it with the property, then solving this particular problem becomes easy. That's the reason why the properties of the functions are very important. If we are very thorough, then within a few seconds we can solve such problems very easily. And now another important property of the impulse function is derivatives. So you have a derivative, first derivative del dash, second derivative del double dash, and so on. It may get extended up to nth derivative. We may generalize and we may find the generalized solution for the nth derivative or kth derivative, which may be useful for us in solving the problems. So you take the simple example, simple equation here, integral minus infinity to infinity del dash t f of t dt, and now it is of the form, if you remember, it is of the form integral uv, and for which the integrand value, if you remember, it is u integral v dt minus u dash integral of v dt dt. So in this case, we can take u as f of t, and integral v dt. In place of v, we have in place of v we have del dash t. So integral del dash t dt will result in a value. It will result in del of t. That is the reason why the first term is del of t f of t, and the second term being integral minus u dash, again within that integral v dt, that will result in integral minus infinity to infinity del of t f dash t dt. And if we substitute and you take the property of integral minus infinity to infinity, del of t value is unity as per the special property of your impulse function. Yeah, so if you substitute those things, you are going to get here the first derivative value as minus f dash of 0, first derivative of impulse, provided f dash is continuous at time t is equal to 0. The del dash is called a doublet. You may have the higher order, like starting from the del dash, del double dash, you may treat all of them as higher order impulses. So you extend the same for higher orders. As a result, you are going to get minus 1 whole power k, and this is the like f dash, because here this is the first derivative, here you got 1. If it is the second derivative, f double dash, that is f2, f superscript 2 I am talking about, again f superscript 3 of 0, and so on. We are here deriving for the nth derivative. So we nth derivative, in that case minus 1 whole power n fn of 0. Now in this particular equation we have shown the kth derivative, and hence minus 1 whole power k fk of 0. So now you will find the use of this particular derivative of impulse function in solving the problems such as like this. Now let us rewrite the equation, nth derivative, integral minus infinity to infinity x of t d by d power n dt of n, that is nth derivative, d by dt nth derivative of delta of t minus t1. So as just now we proved, the nth derivative of this impulse function is going to provide us minus 1 whole power n d by d nth derivative of x of t at time t is equal to t1. And now let us take a example problem based on this particular nth derivative concept. We are given t square plus 3t, which is replicating x of t, which is resembling x of t, and delta dash t minus 2. So as we observe, this delta dash is the first derivative of the delta, hence delta dash t power minus 2. So here we can see that minus 1 whole power n, in place of n we need to substitute 1. Why 1? Because it is the first derivative. If it is second derivative, n is equal to 2. If it is kth derivative, then here in place of 1 you may get k. So d by dt of, as it is a first derivative, of d by dt of x of t. In place of x of t we have t square 3t. So d by dt of t square is 2t and d by dt of 3t is 3. As we are multiplying with a minus 1 value, it is resulting in minus 2t plus 3, and at time t is equal to t1, we need to substitute in place of t1, we have here 2, and if we substitute that value of t as 2, we may get here minus of 2 into 2 is 4, and then minus of 4 plus 3, that resulted in a numerical value of minus 7. So this is an example problem for finding the nth derivative of a given impulse function. And based on so far the different properties of impulse functions, we are given here 5 different problems covering most of the impulse function properties so far we have discussed. I suggest all the students take these 5 problems as a homework problems and try to solve them, and we may discuss the solution of these 5 problems in tomorrow's session. And we will quickly move on to the next important topics, and hence these problems will be given as homework problems. We have done for all the properties so far we have discussed, like the impulse function properties like time scaling, all the properties. Okay, so we have done minimum 2 to 3 problems we did for each and every property. In a similar manner, you can take these 5 problems as homework problems and you may work out, and tomorrow we will discuss the solution for these 5 problems. Okay, and we will quickly move on to the next important standard text test signal, which is called a unit step function. So how do you define a unit step function? The unit step function is denoted by u of t, and it is defined as u of t is equal to 1 for t greater than or equal to 0. So it does exist for all the positive values of t only, and u of t is equal to 0 for t less than 0. You may here try to see the plot of this u of t, and u of t is having an amplitude of 1 for all values of t which are greater than or equal to 0. On the left hand side, you don't find any amplitude value, it is 0. And now you may relate the impulse function or delta function to the unit step function by the relation. By integrating the unit impulse or the delta function, we are able to get a unit step function. We may readily verify this, and the limits are minus infinity to t, delta of tau, d tau. We may easily verify this is a unit step function. And now here is again the plot of unit step signal for continuous sequence and a discrete sequence. On the bottom most, you will observe an equation on the plot which I am highlighting now. U of n is a discrete step signal, whereas this is a continuous one. Whereas this is a discrete sequence, and it is defined as u of n is equal to 1 for all n greater than or equal to 0, and it is 0 for all n less than 0. And you can observe the plot of this discrete sequence given clearly here, and at n is equal to 1 you have an amplitude, at n is equal to 2 again you have an amplitude, n is equal to 3, and so on. You got all the values greater than n values which are greater than or equal to 0, you have the existence of unit amplitude, whereas for all the values of n less than 0, you will observe there is a 0 amplitude. And now another important function is called unit ramp function. And how do you define this unit ramp function? Is ramp of t is given by t, and the t should be greater than 0, and it is equal to 0 for all values of t less than or equal to 0. You may observe this particular ramp function given by, and we are now creating a relation between unit step and as well as unit ramp function, and here is a clear indication of, if you take u of t as a unit step function, integrate that unit step function between minus infinity to t, you may get the unit ramp function as t u of t as a function for unit ramp. Now we can now understand, if I integrate the unit impulse function, what function I am going to get? I am going to get a unit step function, and then by integrating the unit step function, I am going to get a unit ramp. So here we have clearly mentioned the unit ramp function is the integral of unit step function. It is called the unit ramp function because for positive t, its slope is 1 amplitude per time. So what is the meaning of slope 1 amplitude per unit time is, slope is given by the y coordinate divided by the x coordinate. On the y coordinate we have clearly the amplitude is there, and on the x coordinate we have time, and hence we will say amplitude per unit time is the slope. That's it. So it is very simple to understand. Now, so far we discussed that integrating the unit impulse will result in unit step, integrating unit step will result in unit ramp. Now let us take the ramp function and let us differentiate the ramp function. If you differentiate the ramp function, that will result in a unit step function, and now differentiate a unit step function, you may get the unit impulse function. So these are the relations among the ramp, step and impulse signals that we just now discussed. Now let us move on to other kind of signals. Like often you may get sinusoidal and exponential signals. So we may need an understanding of these signals, particularly in signals and system analysis. When we are solving differential equations, you may find the use of these sinusoidal and exponential signals. That's why we are discussing those sinusoidal signals and as well as exponential signals now. The sinusoidal signal a sin omega naught t can be given as omega naught is a angular frequency, and for which the relation between the angular frequency and the linear frequency f naught is given by omega naught is 2 pi f naught, and hence you may find here a sin 2 pi f naught t as the signal, and that can be rewritten as a sin 2 pi by t naught. So the relation between the frequency and the time period capital T can be given as inverse of time period being frequency. We may replace f naught with 1 by t naught, and hence here on the right hand side we have written the equation as a sin 2 pi by t naught multiplied with the t, and the radian frequency can be shown as a sin omega naught. And T naught, why we are very particular about that T naught is that T naught is nothing but the time period of the sinusoidal wave. And let us now again see a sinusoidal signal with a phase shift a sin 2 pi f naught t plus theta, where there is a phase angle of theta involvement is there. We replaced that linear frequency term with an angular frequency called omega naught, a sin omega naught t plus theta, and we may express this in the form of these sinusoidal signals and cosine signals, even in the form of the exponential form. So x of t is equal to a e power a t is a real exponential, because you don't find any non-real term here, whereas a complex term consists of j sin omega naught t term, and the equation for a e power j omega t is given by, let us take it as a e power j theta as a cos theta plus j sin theta, whereas theta is here omega naught t or omega t. And theta is the phase of sinusoidal, where A is the amplitude, F naught is the fundamental cyclic frequency of the sinusoidal, and radiant frequency or angular frequency is given by omega naught. And if you see the plots of the real exponential signals and damped sinusoidals, you may observe one is a rising exponential and the other one is a decaying exponential. For the rising exponential, e power at, observe that a is a positive. When a is a positive, it is a rising exponential function. When a is a negative value, like in the case of x of t is equal to e power minus at, it is a decaying exponential function. So, a discrete time exponential signal can be expressed as x of n is equal to a power n, and that here we have a plot of decaying sinusoidal signal and a growing sinusoidal signal, and these are the two cases when r is less than 0 and r greater than 0, which is with the term r is present in this equation, e power rt. So if r less than 0, that is a negative value. If r greater than 0, that is a positive value. So based on which we may get, when r greater than 0, it is a clear case of a growing sinusoidal. When r is negative, it is the case of a decaying sinusoidal signal. So we may easily understand this one. Another important function, we may use these kinds of functions in communications and as well as in signal processing, and hence there is a need for studying these kinds of functions called signal function, which is represented by Sgn of t, and it is defined, the value of it is defined as 1 for all values of t greater than 0, and it is 0 at time t is equal to 0, and minus 1 for all negative values of t. And hence, you may write in the form of an equation as 2u of t minus 1. And you observe that while defining the signum function, we had made use of a unit which function? Unit step function, u of t. We had made use of unit step in defining the signum function. And you observe there is a precise graph with a precise amplitude and the time. Here, the signum function is closely related to the unit function, whereas the commonly used graph is given on the extreme right hand side with the amplitudes indicated here. Now, there is another important function called rectangular pulse or gate function. So it has two names, rectangular function or gate function. The rectangular pulse, it has an amplitude of 1 by a. You observe on the vertical axis, we clearly indicated the amplitude of 1 by a, and that too for mod t less than a by 2, and for values of delta a of t is 0 for mod t greater than a by 2. And this is how we can define a rectangular function. Now, if we multiply that rectangular function with an amplitude of a, so you observe a rect of t by capital T, you observe here you have an amplitude of a, and your t again is, as here we have a clear indication of minus a by 2 to a by 2. So clearly here we have minus capital T by 2 to capital T by 2. And now if you are asked to plot 2 rect of t by 3, see what is to be done is amplitude being 2, here 3 by 2 is 1.5, so 1.5 we got, and here again minus 1.5. So now the subtract the lower limit of limit from the upper limit, then 1.5 minus 1.5, that will result in a time of capital T of 3. So we can clearly see this rectangular pulse or a gate function. Next is an important function called unit triangle function. So let us try to understand what is this unit triangle function. So a triangular pulse will have a height and area, both are 1, but its base width is not 1. Now you observe it has a height and as well as the area. So height is 1, one can observe, but the base width is not equal to 1. Is called a unit triangle function. The unit triangle is related to unit rectangle through an operation called convolution that we are going to discuss in the next sessions. Time being, we may take the equation for triangular function as tri of t is equal to 1 minus mod of t for all modulus of t less than 1, and tri of t is equal to 0 for all modulus of t greater than or equal to 1. And now you may plot x of t signal as x of t is equal to 2 tri of t by 5, and this is the given unit triangle function, and you are asked to plot that. Then you may easily plot. This is the case of tri of t by 5 and minus 5 and 5 being the limits. So you may easily see this. And there is another important function called sinc function. So we may see the unit sinc function is related to unit rectangle function. Just now we discussed about unit rectangle function through an operation called Fourier transform. This Fourier transform is an important concept, again, which we are going to discuss. Now, one may ask why we are studying these many functions. You may observe the use of these sinc functions in noise removal in the signals. Hence, there is a need for defining these functions, and then they may be used in our future operations of noise removal in the signals. And the sinc function is defined as sinc of t is sine of pi t divided by pi t, and the plot of this sinc function can be seen here. The amplitude being 1 at t is equal to 0 as 1, and for all other time values it is going to vary. So this is the shape of a sinc function, and we are making use of this, we'll make use of this sinc function in applications like communication and signal processing. Now, the sinc function may be related to another function called sampling function that we will discuss right now. Sinc t is given by sine pi t by pi t, and that is SA of pi t, and sinc of 0 is given by sine of pi t by pi t, which is equal to 1. Now, how do you say this value as 1 is you thoroughly know sine theta by theta is equal to 1 for all smaller values of theta is the property that we are using, and hence one may easily say sinc of 0 as 1, that value as 1. If you substitute the value, then we are going to get sine theta by theta as 1 for smaller values of theta. Now, sinc of infinity, a high value, infinite value will result in a 0 value. So, any value divided by infinity value. In the denominator, you may find infinite value, and hence that is going to result in a 0 value. If sinc of t is 0 and sine pi t by pi t is equal to 0, you are here going to have a relation between the t and the n. What is this n is? Here you observe, here this n value is here 0, and here 1, here 2, here 3, here 4, and so on. So you may observe that from the sinc function. And let us take another important function called sampling function. Now, if we take sampling function, just now we discussed that sinc function and sampling function are related with each other. And here we have shown the relation between sinc and sampling function as SA of pi t is same as sinc of t. Now let us take the sampling signal SA of t, which is given by sin t by t as the sampling signal. And if you substitute in the similar case of sampling signal value at t is equal to 0, making use of limit t tends to 0, limit t tends to 0, sin t by t as 1, just we had used the same property of sin theta by theta is equal to 1, limit theta tends to 0 property. And SA of infinity is sin infinity by infinity, and the value of this lies between sine for the possible lowest and highest values of sine functions. You may see that -1 and +1, and then divided by infinity. Anyway, it is going to result in a 0 value. And yeah, and similarly, you are going to have t is equal to n pi. This we have discussed. And unit step sequence for the case of a discrete signal is given here. And here again we are going to have a relation between the impulse function and unit step function. Suppose u of n we want to express in terms of your impulse, and k is equal to -infinity to n delta of k. And as we clearly know that delta of k does exist only from 0 to n. And let us take n minus k as the delta of n minus k, and the lower limit being 0, k is equal to 0 to infinity delta of n minus k. Now you can get a easy relation between delta of n and your unit step function. This is the relation between your unit step and as well as your step function and unit impulse function. Delta of n is equal to u of n minus u of n minus 1. And now let us move on to the classification of systems. Now this is very important for us, and you may get a good number of problems in the GATE exam based on the classification of systems. So already we have defined what is a system. The systems process input signal to produce the output signal. So what is the system is going to do? The system is going to process input signal and it produces a output signal. What is a system is? It is a combination of elements that processes one or more signals to accomplish a function and produces the output. Now, different types of systems we can observe. There are different types of systems: causal, non-causal, linear and non-linear, time invariant and time invariant, stable, unstable systems, static and dynamic, invertible and non-invertible systems. Now, this particular session, we are going to thoroughly discuss whether a given system is belongs to which particular kind of system among these given different types of systems, which is very important, and you may expect a definite question in the GATE exam based on these types of systems. So far, that is what is happening, that we will discuss. Before going to different types of systems like causal and non-causal system, we will try to understand causal, non-causal signals. And here is the causal, non-causal and anti-causal. So often you may find a new term called anti-causal, and most of the students has a doubt: what is causal, what is non-causal, anti-causal, or is non-causal and as well as anti-causal, are they same, or they are different? Now here we are going to get a very good clarity about the difference between a anti-causal system and a non-causal signal, and you may observe very clearly from these plots causal signals exist for t less than causal signals are signals that are zero for all negative time. Okay, so for all negative time here, for all t less than zero, you can you observe here any signal? No, the signal is zero here. For all values of t greater than zero, you have existence of signal. So we are defining causal signal as f of t is equal to zero for t less than zero. Now let us define anti-causal. Anti-causal are signals that are zero for all positive time. F of t is equal to 0 for t greater than or equal to 0. And you observe here for t greater than or equal to 0, you don't have any signal on the right hand side, whereas the signal does exist on the left hand side. Now let us go for a non-causal signal. Non-causal signals are signals that have non-zero values in both positive and negative time. So you have, for every t value there exists a signal value. So both on the left hand side and right hand side of your y-axis you have a non-zero value that you may say that as a non-causal signal. Now here listen carefully. I am going to give you a simple tip or a trick to remember the causal and non-causal signals. In nature, whatever the systems are there, whatever the systems that does exist in the nature, they are all causal in nature. Now, what is meant by they are all causal in nature? Whatever the systems that are there, they don't anticipate any future input. That means the output of that system does not depend on the future values. For example, take a case of an electronic appliance or an electrical appliance. For example, you have a fan. Now, you are going to switch on the fan, say after 10 minutes, anticipating that you will switch on the fan after 10 minutes, the fan will not start rotating now. That means your system is a causal system and it is not anticipating the future input values, and hence you may understand that whatever the systems that are there in the nature as causal signals, and whichever the systems that will anticipate and whichever the systems that depends on the future input values are said to be non-causal. This is how we can easily remember causal and non-causal signal conditions. Why these tips or tricks are required is we are going to discuss about the properties of more and more number of signals. If we understand such examples, you will not forget the property at all forever. That's the reason why it's important to have such simple and easy properties that one can understand thoroughly, so that it becomes very easy for us. So now let us define a causal system. A system is said to be causal if the present value of the output signal depends only on the present and or past values of the input signal. So there is no mention of the future input signal in the causal system. That clearly indicates causal system does not depends on the future input values. And let us take an example. We have an example of y of n is equal to x of n 1 by 2 x of n minus 1. This is one example. Now let us take another example. Y of t is equal to x of t. Now always your output y of t value will depend on only on the present values. Y of t is equal to x of t minus 1. That means here you observe that your output y of t depends on the past value. And now take the case of y of t is equal to x of t plus x of t minus 1. This is an example case where your output y of t depends on the present and as well as the past values. The present value being x of t and the past value being x of t minus 1. Now, let us take the non-causal system definition. A system is said to be non-causal if the present value of the output signal depends also on the future values of the input signal. Now, in the equation, it's a clear case of y of n is equal to x of n plus 1, 1 by 2 x of n minus 1. So here you will observe that there are examples for both discrete sequence as well as continuous sequence, which are t in nature. They are your continuous, and wherever n is there, you can understand they are discrete sequences. Y of t is equal to x of t plus 1. So it depends on the future value, the output signal. Which one? Output signal depends on the future input values. X indicates input, y indicates output. Y of t output depends on the future input values, and hence it is a non-causal system. Now let us take the other example. Y of t is equal to x of t plus x of t plus 1. Again here clear case of that your output depends on the future values. Here this term indicates the past input value, whereas x of t plus 1 indicates the future input value. Again, you have an equation. X of t is a present input value, x of t minus 1 is a past input value, and x of t plus 1 is a future input value. So in all the four equations of the systems, you will find there is a common x of t plus 1 term, which clearly indicating that the output is dependent on the future input values. So we can easily identify a non-causal system if the output depends on the future input values. So here is 9 different examples of causal and non-causal systems. Suppose we are given y of t is equal to x of 2t is the first problem. Y of t is equal to x of minus t is the second problem. And y of t is equal to x of sin t is the next problem. And fourth problem is y of t is equal to x of 2t and y of t is equal to x of t minus 1 for t greater than or equal to 0. And fifth is you have odd of x of t, that is odd part, odd and even even portions of x of t we discussed in yesterday's session. So now you will find the use of finding the even portion and odd portions now in solving. Whenever such problem is given, you will find the use of them. And now sixth question is y of t is equal to sin of t plus 2 x of t minus 1, so and so on. So now let us take one by one these problems and try to analyze whether the given system is a causal system or a non-causal system. Now first one, y of t is equal to x of 2t. Now just this can be done in a very simple manner. I am giving you a simple solution. Just you substitute t is equal to 1. So if you substitute t is equal to 1, y of 1 is equal to x of 2. Now the system is said to be, it can be identified as non-causal. What is the reason? The reason being, like your output, present output, this depends on the future input value. If it is the case of x of 1, you may say present input, but x of 2 is a future input value. Now y of t is equal to x of minus t, and now substitute t is equal to minus 1. Y of minus 1 is equal to x of 1. The system, again, this system is also non-causal because the output is dependent on the future input value, and hence one can easily say it's a non-causal system. Now take the case Third problem, y of t is given as x of sine t. Now you may substitute the value of t as minus pi. Okay, and if you substitute, see now what is to be substituted, this comes by practice. See, for as it is a trigonometric function, generally what is to be checked for all the trigonometric functions are like the angle values, for which we may have the different values of the trigonometric function, like sine t. You may observe that if we substitute the value of t as minus pi, yeah, pi is 22 by 7, and it is taken as minus pi. We clearly know sine minus pi or minus sine pi is being 0, x of 0, and the y of minus pi. Minus pi is minus 3.14. So your output is dependent. Here this is a negative one. That means the your output is dependent on the future values. X of 0 is again a future value, and hence you may say that the system is non-causal. Now, take the case of here you observe that the time conditions are given. Y of t is x of 2t for t less than 0, whereas y of t is x of t minus 1 for t greater than or equal to 0. So we should be a little bit cautious in noting down y of t is x of 2t for t less than 0. Now let us take t, any value of t that is less than 0. So we can easily know that t is equal to minus 1 is a value that is definitely less than 0. Substitute that value in the equation for y of t. So by substituting that, y of minus 1 is equal to x of minus 2, x of minus 2. And similarly, for t greater than or equal to 0, what is the value of t greater than or equal to 0? So you can take any value which is greater than or equal to 0. Let us take a simple case, t is equal to 1, y of 1 is equal to x of 0. So in both the cases, we observe that our output depends on only on the past values, on the past input values. Hence, we may conclude that the given system is a causal system. Now, let us take the fifth problem. This is what I told, like y of t is odd part of x of t. So odd part of x of t, yesterday we have defined odd and even portions of a given signal x of t as even part as the average x of t plus x of minus t divided by 2, whereas the odd part of x of t is defined as x of t minus x of minus t by 2, that is the odd part of your x of t, and that equation we have taken. Now we will substitute t as minus 1. So y of minus 1 is going to result in x of minus 1 minus of x of minus 1. See, in place of t here we will substitute minus 1. Already here minus 1 is there. Minus 1 gets multiplied with the t value of minus 1. That will result in a plus 1 value. And this is a clear case where our output is dependent on the future input value, and you may conclude the given system as a non-causal system. And now y of t, sixth question. Let us take the sixth question. Y of t is equal to sine of t plus 2 multiplied with x of t minus 1. Now, if you substitute the value of t as 1, you may observe that y of 1 is equal to sine of 3, and t being 1, 1 minus 1, that will result in x of 0. And sine of 3 is a constant coefficient, and x of 0 being the past value, you may say that your y of t, that output is not dependent on any future values. You observe here, though in the sine function you have t plus 2, because you are computing that numerical value, you are substituting, that will result in a numerical value, and hence you need not worry whether it is a causal or a non-causal, and you need not get confused. It is a clear case of system as a causal system. Now, let us take again another question, seventh question, which is given as y of t is equal to integral minus infinity to t x of tau d tau. Now, t plus 1, you may see that the present output value depends on the future value. In place of t, if you substitute t plus 1, y of t depends on x of t plus 1. Hence, the present output depends on future values also. Here, it is a case of non-causal system. Now, let us take the ninth problem. The ninth problem is given by y of t is equal to integral minus infinity to 2t x of tau d tau. And now, if you try to solve this problem by substituting the upper limit of your integral, which is 2t, in place of t, so you will find y of t is equal to x of 2t, and there is a dependency on the future value. Just substitute t is equal to 1, y of 1 is equal to x of 2. So x of 2 is a future value. Present output depends on future value of input, hence the system is a non-causal. Now, the other important classification of the system is, so far we discussed about the causal and non-causal systems. The other important classification of the system is linear and non-linear systems. So now let us try to understand what is a linear system. A system is said to be linear if it satisfies the principle of superposition, or it can be divided into two important properties of homogeneity and additivity. So we have to check whether the given signal is satisfying the homogeneity property and additivity property. Let us try to understand the homogeneity and additivity property. For the first property, we will take it as additivity. So consider a system with an input x1 of t, and if we apply x1 of t as the input for our system, the output obtained is taken as y1 of t. Now, we applied again a different input than x1 of t. Say we applied x2 of t as our input, then that produced an output of y2 of t. The system is said to be additive, and if and only if an input of, now we are going to add both the input signals x1 of t and x2 of t, x1 of t plus x2 of t, and apply this as an input signal to our system. Then if we get an output as the sum of the two outputs, like y1 of t and y2 of t for all possible inputs, in that case we may say that the system is satisfying the condition of homogeneity. Now, additivity, it is the case of additivity. Now, let us take the homogeneity property. The homogeneity means that a change in the input signal's amplitude results in corresponding change in the output signal's amplitude. Then we may say that it is satisfying the homogeneity property. Let us take the input signal x of t, and if we apply that input signal x of t to a system, and the output of the system is y of t, and now multiply the input signal by a constant c, and then if I multiply my input signal x of t with a constant c, that will result in a c into x of t. Now apply c into x of t as the input signal, that may result in an output signal of c y of t for any input signal where C is a constant, as we already discussed. So these are the two properties, and we will represent these two properties in a simple equation form. The two input signals x1 of t and x2 of t are added, and the added signal is applied as an input. If it results in the individual output, summation of the individual output signal values like y1 of t plus y2 of y2 of t, then we may say that the property of additivity satisfied. Now, you take the input signal x of t, multiply it with a scaling factor or a constant, and then apply that as an input signal, that scaled input signal as an input signal to the system. You may observe that here you got cy of t, which is an output signal. Now, if you combine these two properties, that becomes the superposition. So how do I combine is x1 of t plus x2 of t is additivity, and homogeneity is multiplying or scaling with a constant. So I am multiplying with a constant a, the first input signal. The second input signal I am multiplying it with b, and if this signal a x1 of t plus b x2 of t is applied as an input, and if it is resulting in a y1 of t plus b y2 of t, then we will say that the superposition principle is satisfied, and we may say that the system is linear. So for linearity, and let us do a simple calculation for a simple analysis for the linearity. For linearity, the output should be 0 for a 0 input. There should not be any non-linear operations. So let us try to understand non-linear operations. If our signal or the system contains the functions like all the trigonometric functions like sine, cosine, tan, cot, secant, cosecant, or logarithmic functions, exponential functions, modulus, square, cube, root, sampling functions. Just now we discussed about sinc functions, signal functions. So all these will have non-linear operations. So it is a clear case of identifying the linearity. So if there is involvement of such functions in our system, we may easily identify whether it is a linear or a non-linear, the condition being there should not be any non-linear operation. So now we are given a simple problem. Y of t is equal to x of t plus 2, and we are asked to find whether the given system is a linear system or a non-linear system. So you take the input. First input x1 of t, corresponding output is y1 of t. Second input is x2 of t, corresponding output is y2 of t. Now take the additive property, add x1 of t input signal with x2 of t, again another input signal, then the output must be y1 of t plus y2 of t as per the additive property. Now y1 of t is x1 of t plus 2, and y2 of t is equal to x2 of t plus 2. If I apply x2 as your input, now take the summation of these two, that is x1 of t plus x2 of t, and if it is resulting in the same value of y1 of t plus y2 of t, then you may say that as a non-linear. Now try to compute x1 of t. Y1 of t is just now we had taken it as x1 of t plus t 2. So substitute in place of y1 of t x1 of t plus 2. In place of y2 of t, you may substitute x2 of t plus 2. As a result, we got x1 of t plus x2 of t plus a value 4. If we might have got x1 of t plus x2 of t, it is a clear case of linear system. But whereas we, in addition to x1 of t, y1 of t plus y2 of t, other than y1 of t plus y2 of t, we have here x1 of t plus x2 of t plus the additional value. Hence, it is a clear case of a nonlinear system. Now, let us take again another example. Y of t is equal to x into sine of t, x into sine of t, and y1 of t is equal to x1 sine of t, x2 sine of t. Similarly, you can apply both the additivity property and as well as the homogeneity property. So the additivity property is like your y1 of t, which is x1 of sine t plus x2 sine t. Now y of t is x1 of sine t plus x2 sine of t. Now you may add y of t is clearly y1 of t plus y2 of t. The additivity property got satisfied. Fine. Now let us check for the homogeneity property. To check the homogeneity property, that your input gets multiplied with a scaling factor. We have taken the scaling factor as k into x of t. So in our case, our input signal being x sine of t, so we can multiply that with x sine of t, and k y of t is simply x sine of t. So k into x sine of t. So you may observe k into y of t is same as k into x of t. Hence, the system is said to be a linear system. Now, take another classification of the system, that is time invariant and as well as a time variant system. A system is said to be time invariant if time delay or time advances of the input signal leads to identical time shift in the output signal. Now, let us take a system diagram. A system with single input and output signal is shown here. And a system is called time invariant if a time shift in the input signal. So x of t is our input signal. The time shift in the input signal is indicated by x of t minus t naught, and it causes the same time shift in the output signal y of t minus t naught. Then we may say that the system is invariant. So you observe the first figure in which you applied x of t. The resultant output signal is y of t. Now apply a time shifted input signal. So the time shifted input signal is represented by x of t minus t naught. And for this system, if I apply the time shifted input signal as my input, the output is also time shifted. So that is y of t minus t naught instead of y of t. Hence, the system is said to be time invariant. Now, let us try to understand by different examples. You are given a problem. Determine whether or not each of the following systems are time variant with input x of t and output y of t. So you are given whether the given systems are time variant or time invariant. Now observe the first signal. It is y of t is equal to t into x of t, and the second one is y of t is equal to cos t x of t. That is the second system equation given, and you are asked to find whether it is a time variant or time invariant. And the third system equation is given as y of t is equal to 2 plus x of t. Now you need to find whether they are time variant or time invariant. Just you take a few seconds time and then try to recollect the property of your time invariant. For a time shifted input, the output is also time shifted, then we may say it is the case of time invariant. Now we will try this particular problems. Y of t is equal to t into x of t. So delay the input by a factor of t naught. Y1 of t is equal to t into x of t minus t naught. That x of t got delayed by a factor of t naught. We discussed delay in time, advance in time in the properties of the signals in the yesterday's class. We are making use of that now. Delay output by t naught, let the output be y2 of t. y2 of t is equal to y of t minus t naught. That means we are delaying the output, and we need to substitute wherever t is there. We need to substitute t minus t naught in that equation. We know the given equation is y of t is equal to t into x of t. So we are substituting in place of t minus t naught. So here in place of t we have t minus t naught. Again in x of t equation in place of t we have t minus t naught, and we can observe that for a delayed input signal we are not getting the same delayed output signal, as y1 of t is not same as y2 of t. Hence the system is said to be a time variant system. If this condition of y1 of t is equal to y2 of t gets satisfied, then the system is a time invariant system, whereas as the condition is not satisfied, we are concluding the system as a time variant system. Now let us take the second problem of identifying whether the given signal is a time variant or a time invariant. So y of t is equal to cos of t, x of t. Now delay the input signal by a factor of t naught. So cos of t, x of t gets delayed by a factor of t naught. So we did that. So we got y1 of t. Now delay the output signal by a factor of t naught. So y2 of t is equal to y of t minus t naught, and hence you have to, wherever t is there, you have to replace it with the t minus t naught. So again we do not get the time delayed input signal is resulting in the same time delayed output signal. y1 of t is not equal to y2 of t. Hence the system is time variant. Now let us take the third problem. Y of t is equal to 2 plus x of t. y1 of t can be computed as 2 plus x of t minus t naught, and now y2 of t we may compute by delaying our output signal y of t. Now delay the output signal y of t, so it is y of t minus t naught, that is resulting in 2 plus x of t minus t naught. Now in this case we got y1 of t same as that of y2 of t, hence we may say that the system is a time invariant system. Now another important classification of the system is stable and unstable systems. Now let us define a stable system. How do we define a stable system? Is a system is said to be bounded input and bounded output stable. So in a short form we will say BIBO stable, bounded input and bounded output stable, if every bounded input results in a bounded output. So we may take the equation for this. Let us say mx is our bounded input value, and as it must be bounded in nature, the value of that should be, must be less than infinity. So if you take mod of x of t, which is a input value, that must be less than or equal to mx, which is a value, and that must be less than infinity. And for every t, y of t, which is a output value, less than or equal to my must be less than infinity. That means that both the input and output values must be finite values. If they are infinite values, they are not bounded either in input or output. Then the system becomes unstable. So it is very easy to identify whether a given system is stable or unstable just by checking this for a bounded input, for a given bounded input values, whether we are able to get a bounded output values or not. If we get, then we may say that the system is stable. If we do not get the bounded output value, we may conclude that the system is an unstable system. Now, let us take a simple example. A discrete sequence y of n is given 1 by 3 of x of n plus x of n delayed by 1 unit, that is x of n minus 1, and x of n delayed by 2 units of delay, that is x of n minus 2. This is the given system equation, and you need to find whether that system is a stable or an unstable system. So 1 by 3 x of n minus 1 plus x of n minus 2. And now we may take x of n value, and for any values of n, x of n will lie as we will be having a finite value mx, say mx value, x of n minus 1, let us, it is also having a finite value, again mx. So 1 by 3 mx plus mx plus mx. So mx is nothing but a finite value we are taking, 3 mx divided by 3, as it is resulting in a value of mx, and this is a finite value. If that mx is less than infinity, then we may say that it is a stable. If mx is not less than infinity, then we may say that the system is unstable. Now, we will take an example. Suppose the system representation equation is given by y of t is equal to a into x of t. We may say readily this system as unstable. Now, let us examine why we are saying it as an unstable system. If you consider the case where a is greater than 1, and you assume that x of t is a unit step function. Just now we discussed u of t is equal to 1 for all t greater than 0. So let us assume that x of t is u of t. Then at every instant u of t will keep on moving, keep on multiplying with amplitude a, and hence it will not result in a bounded value. You see, this is not going to stop. This process gets continued for all values of t, and this multiplication is going on repeatedly, and hence it will not result in a bounded value, and it may tend to finally an infinite value, and hence we may conclude that the given system with equation a into x of t and x of t being u of t, we may conclude that the given system is a unstable system. Now, let us take again another example. Y of t is equal to x of t plus 2. Now, substitute x of t value as 10. Y of t is equal to 10 plus 2, which is resulting in a value of 12. And we got, for a bounded input, we gave a bounded input value, and that resulted in a bounded output value. We may conclude easily that it is a stable system. Now, take the other example, y of t is equal to t into x of t. Say, x of t, bounded input value, we are giving the input value of 10. And y of t is equal to t into x of t. So, t, there is a 10t term. and the t can be any value. You may have any value for t, as t can be any value of value. That too, it can be a value between minus infinity to infinity. The moment it is a very high value like infinite, our y of t value becomes infinite, and we didn't get any bounded output value. Our output y of t is unbounded, and hence we may conclude that y of t is equal to t into x of t system is an unbounded system. Now, let us take another example. Y of t is equal to x of t by sine of t. Y of t is equal to x of t by sine of t. And we may substitute x of t value as 2. And y of t value can be computed as 2 by sine t. Now, when t value can be substituted as 0 or pi, sine 0 we are aware as 0. Also sine pi value is 0. So the moment the denominator becomes 0, the output y of t value becomes infinite and it is an unbounded output. Hence we may conclude that the output is unbounded, and we may conclude that the system is unstable, not y of t unstable. We may conclude that the system is unstable. Now, there are again another important classification of static and dynamic systems. Now, we may take a static system. A static system is a system for which there is no memory. So, it is a memoryless system and it has no storage devices. Its output signal depends on present value of the input signal, and there is no dependency on the previous values or the storage values, and hence we may say this is a memoryless system. For example, we have a electric circuit with a resistance value, applied voltage V. So I of t is equal to 1 by R V of t. So I is equal to V by R is the equation. A of t is equal to V of t by R is the equation. We may say this is a static system. Now, a dynamic system, it will possess memory and it has a storage device. For example, we have taken a system possess memory. Its output signal depends on the past values and as well as future values of the input signal. Then we may say that it is a dynamic system. So I of t is equal to 1 by L integral minus infinity to t v of tau d tau. We may find y of n as x of n plus x of n minus 1. And now let us take an example problem. You are given a simple circuit that consists of a voltage source v of t, and you have a resistance and you have a capacitance C. We may readily say this as a dynamic one. Now the question is, why it is dynamic? Do remember the case memoryless or memory based. So you have the capacitance here. The capacitance is a storage element. Okay, capacitance is a storage element. So the capacitor, when the power is on, it charges, and when power is off, it discharges. So the system shown above is an RC circuit. Resistance, of course, is memoryless. C is a memory device as it stores the previous charge, because of which voltage across it cannot change immediately. Hence, the given system is a dynamic or a memory system. And now, again, another example, we can see y of t is equal to 5 into x of t integral minus infinity to t x of tau d tau, and then y of n is equal to sigma m is equal to n minus 5 to n plus 5 x of m. You observe that there is a memory requirement, okay, in the above two equations. Hence we may say these are the memory systems. Memory-less systems, y of n is equal to x of n and x square of n. There is no presence of all these are present values, and there is no memory requirement. And now we got a good number of problems, like 6 problems are there, and out of these 6 problems you need to identify whether the given systems are static or dynamic. So when y of t, the first 4 are okay, fine, and when it comes to the fifth one, you observe even part of x of t. This is what I am saying, that whatever the fundamental concepts we had done in session 1 are definitely useful. Okay, and here you will observe that y of t is again a real part of x of t. So if straight away, if the system equation is given like this, then the whatever the concept like even part of a signal, odd part of a signal, real part of a signal, these will be useful for us in solving when such problems are given. Right. Now, the first one, whether it is a static or a dynamic one. So you observe that y of t, the output depends on the present and as well as the previous value. That is, previous value means you need to store that previous value. So there is a requirement for the memory. So the dynamic, it is dynamic in nature. Now come to the second question, y of t is equal to x of minus t. So again it is the case of a dynamic system, as there is a requirement for memory that your output depends on, present output depends on the past input values. And now third problem, y of t is equal to x sine of t. Y of t is equal to x sine of t. And now you may substitute the t value as minus pi. We have already done this, the same kind of problem for the other system identification. So x of sine t, in place of t we may substitute minus pi, okay, minus pi. So that will result in a value of 0, sine pi being 0, x multiplied with x of 0, not multiplication, x of 0. So what is x of 0? It is a future value. So y of minus pi, which is minus 3.14, is dependent on the future value, and the conclusion can be drawn as a dynamic system. Now when it comes to the fourth problem, y of t is equal to x sine t. That is done already. We did that third problem, and fourth problem is y of t is equal to x of t minus 1. It's a simple one that we can clearly identify that our output y of t is dependent on the previous input value, like as it is x of t minus 1. Now fifth problem. The fifth problem is you are asked y of t is even part of x of t. Even part of x of t is defined as x of t, it is the average x of t plus x of minus t by 2, and if we substitute the value of t as 1, we may get y of 1 as x of 1 plus x of minus 1 by 2, and we may say that the system is dynamic in nature, as the present output value depends on the past value. We require memory, hence we may conclude it is a dynamic one. And y of t is equal to conjugate x of t. Conjugate of x of t is represented as x star of t divided by 2, and we may conclude that the system is static, as there is no dependency on the previous input values. So that system is static. So now let us take another classification, that is invertible and non-invertible system. A system is invertible if it has an inverse system, otherwise it is non-invertible. Let us try to understand with an example. Y of t is equal to 2 into x of c. System is invertible, must have an inverse. For any x of t, we get a distinct output y of t, then we have an inverse. Thus the system must have an inverse. X of t is equal to 1 by 2, and y of t is equal to 2 into x of t. Okay, so you take x of t, multiply it with a multiplier. So you take a system, it is a multiplier. So when you apply x of t as an input to your multiplier, it gets multiplied, say with a factor of say this, as x of t is here given as a 1 by 2 y of t. Y of t is equal to 2 into x of t. So you got multiplication. And then inverse system. In the inverse system, you have a divider. Here it got multiplied by a factor of 2. Division is taking place in the inverse system. As a result, you are getting back your x of t. Now, you try to identify whether the given system is invertible, or determine whether the signal y of t is equal to 10 plus x of t, and other one is y of t is equal to x square of t, whether they are invertible or non-invertible systems. This is what we are asked to find. Then let us take first problem. Y of t is equal to 10 plus x of t. Now x of t value may be taken as a numerical value like 2, which is a DC input signal. Y of t is 10 plus 2, so the value is 12. Again, a numerical value. Let x of t is equal to 21. We may take any value for x of t. X of t, if you take as 21, which is also a DC signal input, y of t is equal to 10 plus 21, which is 31. Since different input leads to different outputs, hence the system is invertible. So if we apply different inputs and all the different inputs are giving us different output values, then the system is said to be invertible. When we will say non-invertible is, though we apply different input signal values, it is going to result in the same output. Okay, that means if I apply x1 of t and x2 of t as x of t as one value, say a1, x of t as a2, and then I may find out y1 of t and y2 of t, and if both are resulting in different output values, I may say it is invertible. And if they are y1 of t and y2 of t are the same, then it is non-invertible. Now let us take that kind of case here. Y of t is equal to x square of t. Now you may substitute x of t as 5. Y of t is equal to x of t whole square. So that is 5 square, 25 we got. X of t as minus 5. Now you substitute, which is also a DC signal. The y of t resulted in the same 25. So though once we applied plus 5 as one input, in the second case we applied minus 5 as another input. Though we applied two different inputs, the resultant we got that the output is the same for two different inputs. Since different inputs leads to different same outputs, hence the system is non-invertible. Now let us take the previous gate question that are asked based on the concept of these systems, and let us try to solve these previous gate papers. This is a 2013 gate question paper given. The input x of t and output y of t of a system are related by this equation, and you are asked whether the given system is time invariant, stable and non-time invariant and non-stable. Observe that there are two criteria, two classifications in all the four options. What are they? Time variant, invariant, stable, not stable. So let us try to recollect the properties of a time invariant system and a stable system. So stable is very easy. Bounded input, we may apply a bounded input, and if we get bounded output, then it is stable. Time invariant. So you can observe here by a simple substitution of x of t, let us take x of t as delta of t. We may compute y of t as delta of t cos 3 tau d tau, and it is replaced with we may see important property integral minus infinity to t delta of t. If we integrate the impulse, that will result in a step function. Just now we discussed. See, this is the purpose of having idea of different functions like impulse, step and ramp functions. You may find the use of them now solving here. U of t cos 3 tau d tau or cos 3t dt, and you may substitute the value of t as 0. If we substitute value of t as 0, cos 0 will result in a 1, and we got y of t as u of t. Now, for a delayed input, that means t minus t naught, we may say y of t comma t naught. Now, delay our input also, that delta of t minus t naught cos 3 tau. Okay. Now, d tau is given. So, here we got u of t cos 3t naught, and the delayed output y of t minus t naught is equal to u of t minus t naught, but y of t comma t naught is not same as y of t minus t naught, and the system is not time invariant. Now let us consider the stability case. Integral minus infinity to t cos 3t. So x of t is cos 3t. We may write for our comfort like this. Then as t tends to infinity, y of t also tends to an infinite value. We may conclude that the system is not stable. Now again, we will take another gate question which is given in the year 2011. A system is given by impulse response. What is meant by impulse response? If impulse signal is given as an input signal, then the output signal is said to be impulse response. Response is nothing but the output. H of n is equal to 2 power n u of n minus. The system is, you are asked whether it is a stable and causal. So here again, two categories. Whether the given system is causal, non-causal, stable, unstable. So you have to check for two conditions, two classifications of the system. Now, function h of n is equal to a power n u of n, a power n u of n, and we have defined if mod a less than 1, then we may say it as stable, and it will become unstable if mod a greater than 1. So let us take now the given value of a is 2, a power n u of n. Here we have a value of a as 2, and it is a clear case of mod a greater than 1, and we may say it as unstable. For example, if the given equation is h of n is equal to 1 by 2 whole power n u of n minus 2. For example, just I am changing the given system equation and creating again another new problem. Let us take h of n is equal to 1 by 2 whole power n u of n minus 2. For that case, if we want to find whether the system is stable or unstable, now mod a in that case is 1 by 2, which is definitely less than 1, and now we may say that it is stable. The reason being 1 by 2 whole power n, you may take different values of n is equal to 0, n is equal to 1. So 1 plus 1 by 2 plus 1 by 2 whole square plus 1 by 2 whole cube and so on. So this is a geometric progression series for which you can find by simple equation as the first term divided by 1 minus common ratio as the sum of the geometric progression, a by 1 minus r, where a being the first term and r being the common ratio. So you can find, and if you find that a by 1 minus r, you may get the value of it as a finite value, and you may say that the system is stable. So, but here we have the equation as 2 power n u of n minus 2, where this value of a, which is equal to 2, is greater than or equal to 1, and hence we may say that the system is unstable. So we checked for stability. So what is left over? We have causality and non-causal. H of n is equal to a power n u of n, h of and h of n is equal to 0 for all n less than 0, and this is a clear case of a causal, and hence we may conclude that the given one is satisfying causal and non-stable. So option B, which is a correct one. Now consider a system whose input x and output y are related by the equation y of t is equal to integral minus infinity to infinity x of t minus tau g of 2t d tau. Now this you can try. Which of the following properties, 4 properties, are possessed by the system? And you have some bounded input and bounded output, causal, okay, low pass, linear, time invariant. Okay, anyway, we have not discussed about LTI, linear and time invariant, we didn't do, but still out of the given options, which one best suits our system, we have to identify. So let us take this problem. Here h of t is not equal to 0 for t less than 0. For t less than 0, let us take t less than 0. So you may get x of minus tau g of minus 2 tau d tau, and your h of t is not equal to 0 for t less than, thus the system is non-causal. Again, any bounded input x of t definitely going to give us the bounded output, thus it is a bifostable. Hence we may conclude that the given system is non-causal and as well as bifostable. So the option given is to be properly identified. So again, another gate question. The input and output of a continuous time system are respectively denoted by x of t and y of t. So which of the following descriptions corresponds to a causal system? You are given 4 different relations between the output and the input signals, and you are asked to find out which of the following descriptions correspond to a causal system. Now you have to identify, and yeah, just by a quick look, you may identify the C option is a causal, because out of all the 4, in the option C, our output does not depend on the future input values, and hence you may quickly conclude with one glance, you may quickly conclude that option C is correct, which is a causal system in which the output does not depend on the future input values. Whereas in all other equations of the systems, you may observe that the output is dependent on the future input value. For example, the first case, t plus 4, s dependent on future input, t plus 1 dependent on future input value, output. Again, output y of t is dependent on t plus 5. So hence it is a clear case of dependency on the future input values in A, B, D, whereas in C, there is no dependence of the output on the future input values. Thus, only in option C, the value of y of t at t is equal to 0 depends on past value. In all other system equations, the value of output value depends on the future value. Now, let us take another gate question. Let x of t be input and y of t be the output. Continuous systems match the system properties. So, with the system relations. So, we are given 4 different relations, and you have to identify whether the given system equations are among the P1, P2, P3, R1 may be among the P1, P2, P3. That means y of t is equal to t square, x of t may be linear but not time invariant, or time invariant but not linear, linear and time invariant. So you need to check every relation for 2 classification categories of the system. The 2 classifications are linear, non-linear, time variant and time invariant. I suggest to the students, just take this particular gate question as a simple homework problem, and you may try this. Okay, you may try this problem, and we may move to another important question. So, the Dirac delta function delta of t is defined by, we are given 4 options. Delta of t is equal to 1, for t is equal to 0, it is 0, otherwise fine. Delta of t is infinite at t0 and 0, otherwise. Delta of t is equal to 1 at time t is equal to 0 or 0, otherwise. And integral minus infinity to infinity delta of t is dt is equal to 1. This is the option C. Now let us check option D. Delta of t is equal to integral 0 to infinity t is equal to 0 and it is 0, otherwise, and minus infinity to infinity delta of t dt is equal to 1. We may easily identify that option C is the correct option, as area under the impulse function is 1, which is given by a special property integral minus infinity to infinity delta of t dt is equal to 1. This condition also should be satisfied. We can easily eliminate AB, because AB are not giving the full-fledged conditions. See, we require, if there are two properties, and in the definition need to be complete. It should not be incomplete. We may say that AB are incomplete in nature, whereas C and D has two properties, or say this, but delta of t is equal to 1 for t is equal to 0 is correct, and delta of t is equal to 0, otherwise correct. And then the property integral minus infinity to infinity delta of t dt is equal to 1, and hence we may conclude the option D as correct. Dirac delta function delta of t is defined that t is equal to 0 and it has infinite value at t is equal to, just now we discussed, it has, C can be eliminated as it has unit amplitude here. It has infinite amplitude at t is equal to 0 and 0 otherwise, and minus infinity to infinity delta of t dt is equal to 1. The area of Dirac delta function is unity. So option D is correct. So we are satisfying all. Now we are given a system equation y of n is equal to sine phi by x by n x of n. The system is whether it is linear, stable, invertible. So we need to check for 3 different conditions. One is for linearity, another one for stability, and another one is whether it is invertible or non-invertible. So you have to check for all the 3 conditions. So for linearity, what condition is to be satisfied. For linearity, the superposition condition is to be satisfied. The superposition has additivity and homogeneity property. Additivity property is if two different inputs x1 and x2 are given, the output y of t should be sum of y1 plus y2 of t, y1 of t plus y2 of t. And if that is satisfied, your additivity is satisfied. Ax1 of t plus bx2 of t is applied as an input, then our output should be satisfying the superposition theorem. Then we may say that it is a linear. Then stability applied a bounded input, then we are getting a bounded output. We may say it is a stable, invertible and non-invertible. So we can check here y of n is equal to sine 5 by 6 pi n x of n. Let x of n be delta of n. So y of n is equal to sine of 0. So it is bounded. So we may conclude it is a stable one, linear, stable and non-invertible. So we may conclude very easily these things. So now this completes our session with previous GATE questions being answered, and in today's session we discussed about the system classification, whether the given system is a static, dynamic, linear, non-linear, okay, and then causal, non-causal. So all these system classification, time invariant, time variant. So all these we have done a detailed discussion and problems based on these concepts we had finished. Okay. And tomorrow we are going to discuss about the LTI systems and other important topics. Once again, I thank for giving me this opportunity. Okay, I wish you all the best. And if you remember, I gave you some homework problems. So this particular presentation will be posted in the website where you can download this presentation and then you can try to attempt the homework problems from this particular presentation. I thank once again the authorities for giving me this opportunity, and tomorrow we will meet for the next session.